Okay, you can all read it right here.
Thank you. So hi everyone, as Carsten already introduced me, could you also, before I start, I think that's you, Jennifer. Yes, thank you. So yeah, Carsten briefly introduced me. My name is Erika, and in this talk, you will first take a look here at this zoomed in view of, this is actually the Baltic Sea. So it's all very pixely, but you will see during my talk what we can actually see here in this very zoomed up or zoomed in view. So I will today talk about results from a recent manuscript we've handed in. So the talk of today's presentation is spatial composition of the diahaline overturning circulation in the Baltic Sea. So this is our joint work with my co-workers and my supervisors at IW. And yeah, let us take a look straight away at the outline for the presentation. So first, I will start by giving a short review of what has been done in the Baltic Sea. So what you will be hearing during the talk is the word diahaline. Yeah, that you will be hearing very often. So you also see here that, well, we will be looking at quantities in salinity space and the local mixing per salinity class. So you have salinity popping out and diahaline. And what diahaline means, and will be very essential for the talk, is that you have flow across an isohaline, so a line of constant salinity. So 90 degrees across an isohaline. So that means diahaline flow in this talk. So this short background information we'll take a look at first. I have so many screens to look at, it's nice, but also confusing. So after the theoretical background, we will take a look more at, well, I will introduce different new analytical relations that we have derived theoretically. So we will take a look at this as our first result that I will present. And then we have these small checkpoints during my talk. So this is a symbol that you can see here. And then I will also show the next results on the physical and numerical diahaline exchange flow, and again in the Baltic Sea, and also some new results on the diahaline boundary mixing. And then we will just finish off, or I will finish off my talk with some take-home messages for you. So hopefully there will be something that you can actually remember from the talk, because there will be a lot of theory coming up and a lot of plots. So I hope there will be something for everyone to take home with you. Okay, so let us start with sketches to kind of visualize what has already been done in theory up until now. So again, this is the Baltic Sea. And so this is a very simplified sketch of the Baltic Sea circulation in X. Okay, this is quite slow. So in X direction here, and then Z direction upwards. So this is a very simple estuarine circulation that is taking place in the Baltic Sea. So this is very idealized, of course. But so what is happening is that we have the freshwater discharge, or the river discharge, which comes in the sketch here to the right. And this water is very fresh, so it is light. It will flow in here in the surface layers. And at the same time, we have the inflowing saline water that comes from the North Sea. So that is more heavy and will flow in here along the bottom. And then at some point, these will start mixing, these two water masses, and brackish water. So yeah, this mixture will be returned outside across this transect to the North Sea. So this is a general estuarine circulation that we see in the Baltic Sea. So we have already seen that there is a circulation, and that mixing is very important for the circulation. And then you see the citation here. So we have the reference of Knudsen in 1900, and what he did already a very long time ago is to look at so he found bulk values for the river discharge and the inflowing and outflowing water. And he could just give a general, like one single bulk value for this whole circulation. And he could do that even though, so let's see, this was a long time ago. I looked at this myself. So, well, let's just say that he could find the bulk values and keep it at that. So, but these bulk values, they don't help us to really understand what is happening everywhere for the circulation. So what following studies, so a lot later did, so Wallin started this in 1977, and he, well, in the following study, so this is just adapted from the more recent study by Wang et al. In 2017. So what they did was to look at the single transect in space, and you can see that we already have the salinity axis. So this is kind of the first step going into salinity space. And what we see here is a transport profile at this specific point in space, and where we can also see the circulation then, with the inflowing at higher salinity, so towards the bottom, and then the outflowing above. So this is just the circulation at a single point then. And later still, we had the study by Doss et al., and they looked at a stream function in salinity space. So here, if you take a look at the axis, we have again the x direction that we see here, and then the salinity axis. So we have the highest salinities here at the bottom. So we have, with this stream function, we can visualize the circulation, as you can see here. So this is, you can think of this as taking these transport profiles, but taking a lot of transects and then concatenating them together. And then we have more physical space view of the circulation. Yes.
Left figure.
Of the left figure, yes. I removed the units, but we have the transport, so it should be cubic meters per second.
It's not y as in the right figure.
And the right figures in this one. So in this particular situation, or this particular paper, is a bit different because they have a weird XY direction where they go first in the beginning, they go along the X direction, but then so in the Baltic Sea, it kind of stretches like this and then it goes northward. So then they have this, what do they call it again? The pseudo latitude. So it's kind of a mixture between X and Y. Keep it short. Yes, exactly. Okay, so let us come back here to the last case. So we have the salinity axis and the higher salinity at the bottom, so the inflow here. And as you can see, if the flow would not be diahaline, the flow should be just going along like a single salinity line, let's say. But since we do, so it should be horizontal. The arrow should be pointing something like, this instead, so going to the right here. But we do have also the diahaline component, so flow across the isohaline, which is why we also have a component in the S direction. Yeah, so this is one attempt to look at the diahaline circulation. But in the study, I will show you lots of maps in X, Y direction and on a single isohaline. So that is what is upcoming for you now during the presentation. And as we already saw in this first sketch, we could see that we have the circulation, but the mixing is also very important. So we need to know how we can actually quantify this diahaline mixing. And here we have a similar view again, or the same view in XZ direction. So the sketch again, where we have the circulation, and we can look at the mixing. So in this entire estuarine volume, but bounded by a fixed transect, so as a sketch here. But in the theory, we can also bound our volume as a sketch in the one next to it by an isohaline instead of this fixed transect in space. And in all our theories, it's important that we first I say how we define mixing. And what we do is to define it in terms of salinity, variance, dissipation. So we integrate the mixing here, the mixing per unit volume over this entire volume, but we define it in different ways, or we can define it in different ways. And so that is what you can see here in the formula. And it's weird actually saying it in English. Chi, that's why it sounded weird, thanks. Yeah, we have it defined here with the diffusivity in X and Y direction, so the horizontal and the vertical diffusivity. And you can see that the salinity plays an important role again. Okay, so let us take a look at this mixing further. Yes.
differentiate?
Let's keep that question for after, if you don't mind. Okay, thanks. You might just have to remind me then, if I have forgotten, that I have to answer your question. Okay, so let us continue taking a look at the mixing and how we can actually find a formula for this. So I will not be showing you all the theory of how we derive this, but we can then take a look at the sketch. So we once again have the volume that is bounded by this transect. So we want to look at the mixing inside the entire volume. And that was done in the study by McCready et al. In 2018. And they could come up, after a lot of steps, with a simple formula. So here we have the salinity of the inflowing water mass and the salinity of the outgoing water mass and the river discharge QR. And then in practical or in our model studies, we often have this case in between where we have the isohalines that can start stretching outside our model domain. And then we have this intermediate case where none of these two formulas, so this second formula that I will be talking about now, where none of them exactly fit. But this other formula then was derived a bit later, so by Hans Burchard in 2020. And this is then when we bound the estuarine volume by an isohaline instead of a transect. So this is just going from the two slides here, from this kind of general view to how we actually quantify it in terms of an equation. Now, but we're going to take this even a step further in our study. So first, to understand a bit more these different steps, what we can do is to take a look at this band around a single isohaline, and we can look at the mixing inside this band. So that is, yes.
The previous slide.
Yes. I will go back.
2020.
Yes.
As the salinity, right?
Yes, as the salinity.
So it depends on bits of
yes.
The quantity which I look at, right? Looking at salinity, I could also look at temperature. It's a bit weird, right? That it depends on.
Why do you think it's weird?
Where I put the 0 PSU unit and 0 degree point and so on. If you consider temperature, if I use Kelvin or Celsius, I get different values for your dependent.
I think I'd have to think of your question a bit further for the temperature, but also what I did not mention in the beginning is that for the Baltic Sea, we only look at the salinity since that is important. What is important for the circulation and what controls the circulation, so the temperature is not that important. And these theories were derived for salinity specifically. But yeah, I would have to think about the temperature. I will do that.
Was there some assumption that there's a bulk value or some value subtracted from something?
We will discuss it later. Okay. Okay, so we were at this slice around a specific salinity. So we have the mixing inside the specific slice. So that is something we can look at as well. So then we take that's this first relation here. So we have that's a small m of s, the mixing inside the slice. We can derive that by using our integrated mixing in the entire estuarine volume, but then looking at it only in the slice. But what we can also do in the next step then is a sketch right next to it, is that we look at the mixing inside a specific water column. So that's sketched here in this turquoise color. And that is what we call the local mixing per salinity class. So you can just think of it as local mixing for now. And we will look at this more in detail, and I will also show and hopefully make you understand a bit or gain some basic understanding of why we look at this and why it's important, etc. Do you have a question, Trideep?
Yes, I had
Yes.
two. So the first one is, so for the diahaline incoming outgoing velocity, it should be perpendicular to your to the surface the diahaline surface, or the isohaline surface you're considering it everywhere, right? In your figure, it seems like it's not perpendicular everywhere.
Can you try speaking up a bit, Tridip, please?
I'm sorry. Yes. So I was wondering, so I was looking at the second figure, and I was looking at the incoming and outgoing diahaline velocity. So I was thinking from the arrows, I assume it should be perpendicular to the isohaline everywhere, right? But in this case, it seems like not.
Yes, that's you have a good eye. And it's on purpose. So I do talk about diahaline, but we really look at the vertical, kind of a projection of the diahaline direction to the vertical one. So the kind of the vertical diahaline velocity. And that has reasons. And yeah, I was thinking if I should go into that now, but let's just do it. So it makes it easier to make the theory, the calculations, because then, you know, the isohalines, they have, well, if we would look at the diahaline direction, the direction would change all the time, since the isohaline is not a flat line, but it moves and is kind of, has this shape as sketched here. But if we look at the vertical direction, then it's easier to do the theory or do the calculations in themselves, because then we do not have this change of direction all the time. So that's the reason, to answer your question.
Okay, I will think on it a bit more. My second question was, maybe now or later, if you could repeat, the earlier question that was asked about temperature. I actually could not hear it properly, so I was hoping if later on, maybe when you're done, you can repeat what the question was about temperature.
Yes, I will try to do that.
Thank you.
Okay.
Erika, the two M's are different, right?
Yes. Yeah, the two M's are different. So the small M here, that's the one that's sketched in here, but this was my fast solution in the train on the way here. So the M that you see here is the same as this one. And that's the integrated mixing, but inside this slice. And then the other normal M over here is the one that we see at a single point on an isohaline. So inside the water column. So yeah, those are the two different M's. So there are a lot of different M's to keep track of. And I've been working on this theory for some time, and it's still a lot to keep track of. So now we look at the local mixing per salinity class. And here you see how the three mixing quantities are connected. And we will now take a look at other quantities, so diahaline quantities in salinity space. So I work a lot with sketches, so I hope that they help to get kind of a general view of what the idea is of the different quantities and the theoretical steps. So once again, here we have this slice or this XZ directional idealized sketch of the situation. And here we have again an isohaline, and we have different terms here. So we're looking at the water column below the isohaline in this case. And you have to imagine that in reality, this is just, 1 point in the model. So it's really I've exaggerated the distance between the two to just be able to visualize it in this sense or in this way. So what we are looking at is the volume balance of this package that we have here. So the water column below the isohaline. And we have the horizontal volume flux coming in, but we also have the diahaline velocity. And then this position of the isohaline can also change in time. So we have the thickness then between the bottom topography and the isohaline, which is this term here. So this is just the visualization of the volume balance. And if we write this down as an equation, it would look like this. So here we have the same terms again. So we have the diahaline velocity that is here at the third term in the equation. Then we have, let's see, I did add some, effects. So the first term here is the temporal evolution then of the thickness below the water column, below the isohaline. So the thickness of the water column below the isohaline, and how it changes with time. Then we have the second term, that is the divergence of this horizontal volume flux. And all these together then, so if we calculate these first two terms, we can find out what the diahaline velocity is. So I added volume flux here in parentheses, since this is just in x direction, but we actually have this in both x and y direction. So it would be in the end, it would be the volume flux. And there is a lot behind this equation. So this is just to give kind of an idea. But for example, just to show you a bit what is behind in this first term, to find out what the d is here, so the thickness, what we do is to start at the bottom topography, and then we take the layer thickness of a single salt class. So let's see, we have the layer thickness of our salt class, and then we add them up for all the different salt classes until we come up to the isohaline, and that's how we find our thickness. So just to let you know that there are other calculations behind these terms as well. Okay, so this is what we do for the volume balance, the local volume balance, and we can do the same steps slightly differently for the salt balance as well. So here you have the very similar sketches again, but the visualization is the same, but what we have now instead is the salt flux, for instance, and we also have now the salt content inside the water column below the isohaline. So that would be the first term here. And yeah, we still have these three big terms, but the difference now is that since it's salt, we also have the diffusion that is taking place. So we have the JX term here. So that's, yeah, what we have in addition. And also, as you can see here, the advective, but then the diffusive diahaline salt flux. And together they are the total diahaline salt flux. Yes, Tridib? I see that you have a question.
Yes. So for your isohaline surfaces, I see it's a pretty it's a strong curve, and I was wondering do you need to do some sort of interpolation to get the velocities on them, or you just take the values from the nearest cell wherever your velocities are defined? Because I see strong curvatures and inflection points. And then I assume that I don't know what grid you're using, but I'm assuming it won't neatly pass through all your velocity discrete points, right? So if you is there any sort of interpolation involved in this case, or?
I'm not sure I heard the second, so towards the end, but I will start answering. So the curve of the isohaline here, it's just to kind of, yeah, it's a bit exaggerated, but what we really do so what you can really have in reality is not this, okay, I was going to say something that I would contradict myself with. So this is just to make a sketch out of the idea, but what we can have in reality is a far more complicated curve actually for the isohaline. So we can have a curve that kind of goes, yeah, kind of like an S.
Okay.
Let's do it like this. So we can have a curve that goes like an S.
Okay.
And so this is really something that we include in our theory. And we do, so just to keep it short, we can take care of different shapes of the isohaline. So depending on if we have a stable salinity distribution or not. So in practice, we often do not have a stable salinity distribution. So just to say that we do take care of this, and the way it is theoretically done is with the so-called Heaviside function. So that kind of picks out the volume we're looking at. If it's, well, actually, this is a kind of long answer to give in the middle of the presentation.
Right, it's okay. I'm sorry, I don't want to interrupt you. Please continue. Maybe later on, if we have time, you can tell me.
Okay, then I can go into more detail.
Yes, thank
but
you.
The short word is the Heaviside function. And I was also coming back more towards your actual question, I think, but yeah, let's just continue here.
This is the dia-neutral velocity, which you call dia, or the vertical velocity. I think it's vertical.
Okay, so since we already had the question by Tridib in this direction, so here, this is you can see that So I do call it the diahaline salt flux, but you have the additional comma Z that you can see. And this is again, then that's why it's also sketched. Okay, in the sketch, you can't see it that well, but here it's supposed to be in the sketch already, the kind of this Z direction. Exactly. So yeah, if it would really be wrong one. Yeah. So this is this exact what I meant when I answered 3D before. So this is what we do in reality. Okay, so to just summarize this again, we also have the diffusive part that comes into the local salt balance. And what we're interested in is to really find out about the diffusive diahaline salt flux. So as we did for the volume balance, what we do is we want to find out the diahaline velocity, and then we calculate that so we rewrite the equation to find that out. And we do the same for the salt balance as well to find out what the diffusive salt flux is.
What volume flux is it not supposed to use vertical velocity? Was there an interpolation issue?
What do you think if we do all your questions at the end of the talk? Is that okay?
Or just say yes or no? Is it vertical?
But it's just that I have to think for a second, so I do not give a false answer. And yeah. Yeah, but I won't want to try to answer if I do know, so. Okay.
I think it's the vertical.
Yes. Okay, so what we have seen up until now in my talk are a lot of different diahaline quantities. So you saw the small m, so the local mixing per salinity class. You also saw the diahaline velocity and the diffusive, so the diahaline diffusive salt flux. And in all these different studies, and also in Knut's and mine recent manuscript that we have submitted, we derive all these. So they're not easy to derive like this, so I will just give them to you now. But we do see that these different quantities are connected with each other in these three relations, and they have been derived analytically. And what I want to show you now is what they look like in a discrete numerical model. So we will take a look at that now. And here we have the first relation, so between the diahaline velocity and the divergence of the diahaline diffusive salt flux. So here we have these maps of the Baltic Sea, so in X and Y direction. And you can see that it is for the salinity or the salt value of 5 grams per kilogram. And what we have in the upper panel is the diahaline velocity, so on the left-hand side of the equation, and then below we have the right-hand side of the equation. So this is what you can already see is where we have values. So where it's red and blue, that's where this isohaline actually exists. So this isohaline surface in the instance is X and Y direction. So you can see that 5 grams per kilogram, it's already very fresh and it's very far up north in the Baltic Sea. But when we take a look at other salt classes or isohaline surfaces, we can see that it actually moves further southwest into the Baltic Sea. So the salt Baltic Sea is very fresh in general compared to the world ocean. So 11 grams per kilogram is already very high or very saline for the Baltic Sea. So that's why you can see that here it's already here in the Belt Sea. And what we want to do then, so in our model, we have calculated these two quantities separately, and now we want to see if it looks nice in reality. So when we try to look at or try to verify these relations. And as you can see here from all these panels, we can see that the overall picture is actually is as we want it to be, very similar. There are differences, and I will go into the differences more after I've shown you the results from the three relations. But yeah, just to show you what it looks like for these three chosen salt classes. We can also look at other ones, but there are a lot of salt classes, so we have to choose some in order to visualize it. Okay, and here we have the second relation. So between the diahaline diffusive salt flux on the left, so in the upper panel, and the total mixing per salt class in the lower panels. And once again, we have a very similar picture. Here, actually, these are supposed to be exactly similar or exactly the same. So we can also see this from the results here that they do look very similar. And the third relation that we have is between the diahaline volume flux, or the diahaline velocity, sorry, and the salinity gradient of the local mixing per salinity class. Yes, Jidip? Do you mind is it something for the actual slide now?
Yes.
Okay.
So just for the previous slide.
Okay.
So for the middle figure, right? I mean, based on the equation, they should be like almost exactly the same except for their absolute magnitude, right? But in the middle figure between the top and bottom plots,
yes, there are differences. I wanted
Yeah.
to mention the differences. So these the reasons for the deviation that we see after showing the three relations, since it kind of applies to the three relations put together. So I just wanted to show with these slides that the overall picture is very similar, but there are some slight deviations. So if you let's say, wait 2 more minutes, I will answer the question in more detail.
No worries.
Okay. So here we then have the last equation. And we do see the same figure. So the same overall picture. We do see that, for example, for the salinity derivative of the local mixing per sol class, that is here the picture is enhanced in comparison to the diahaline velocity. But then the diahaline velocity is also a bit more noisy. So there are these deviations. And we did see overall that these three relations are similar, but we have also assumed in this the theoretical derivation of the relations so there we assume that we do not have any horizontal diffusive fluxes. So that plays a role for the first and the third equation here. So there we should have, so in this first relation, we should also have the horizontal diffusive fluxes, but we do not look at them here in the model. And
the first equation had them like Jx also Jx. But
yes.
for the calculation, you excluded that.
Yes. I think Knut wants to answer that, but maybe after. Or
I would just confirm your yes. So, I mean, just to give the background, because in literature you only see, I mean, the first relation is always shown in the literature, but in an integral form.
Yeah.
And so this is now the local relation, and now we check, I mean, how valid this local relation is in reality. And because when you do the global integral, I mean, then the horizontal diffusive fluxes pop out, of course. But I mean, and when we are looking at local water columns, of course, then there is a divergence of. We can do so, sure.
yes. Okay, so in the first relation, I just remember that the people online, you probably did not hear the exchange. Okay, great. Okay, so in the first relation, we have neglected the horizontal diffusive fluxes. And in the second, there are nothing that we have neglected. That's why it is exactly equal. But then the third equation here, that's actually we find that by combining the previous two relations. So that's actually a trivial step or an easy step to carry out. But that's also why we have this assumption that flows into this third relation. And that's also one of the reasons for the deviations that we could see. But there are also other deviations. So all these relations, they are analytically derived. So we also have some deviations because of that we're just simply looking at discrete data. But then it is also because the salinity bins. So when we, for instance, when we calculated the layer thickness and we summed it up into the isohaline, then we do that for all these salinity bins. And it can be that they are not filled enough. So then that means they do not have a lot of entries in that specific salinity class bin. And then when we take the mean value of this, it's enough when we just have one value that's completely, very far off, and then it changes the mean value a lot. So that can also be one of the reasons. And then also that we have, so in our post-processing, I calculate the derivatives, and then we can also have discretization errors because of that. Philippe?
So one question I was thinking, so yeah, in your case, so the examples or like the setup was where you have this exchange flows sort of thing. So you will have a very strong vertical component, right? But I was wondering, like, you know, if it's another test case, will the assumption of, you know, neglecting horizontal diffusive fluxes, will it be still negligible? Or like, I mean, will it still hold in your approximate relation, or will it cause any problem? It was just a thought. Maybe you can think about it and tell me.
Yeah,
Like,
we'll think about it. Not something I can answer easily straight away. But
okay.
I will think about it. Okay, so this is what we saw up until now in my presentation. And now instead of looking at all these local quantities, we can also integrate them over the entire basin of the Baltic Sea. So then we get this curve here. If we do this for the diahaline velocity, so then we have the integrated diahaline transport. And what we see basically in this figure is that we have the peaks at 7 grams per kilogram. So that's where the strongest circulation is taking place. And this is not a figure I show in my presentation, but we have it in the manuscript. So actually at 7 grams per kilogram, that's also where the isohaline surface is the biggest. So this coincides with seeing the strongest circulation taking place where the isohaline surface is the biggest.
What is biggest?
Biggest in the sense of really the spatial extent.
From left to right, so to speak, because vertically it always goes through, right? But you.
So vertically, it's just for, so it's the isohaline surface. So the surface of, of an isohaline. But it's kind of like you don't only have one. So you have, for instance, 5 grams per kilogram. So you don't have the vertical direction. So it's just like really like a surface that's kind of shaped weirdly, stretching through the Baltic Sea. But in the end, it's what, let's just go back for a second. So it's, for instance, just the surface here. So if you sum all these values here together, that would be the isohaline surface. And it's actually biggest, well, in this scenario at 7 grams per kilogram, that's where it's biggest. And that also coincides with where we have the peak in this figure. And what you also see in this figure is that, so we can see that the outgoing diahaline transport is bigger than the incoming. So the net outflow, which is actually here the residual, which is negative because the outgoing is bigger than the incoming, equates the incoming freshwater volume. So that is the gray dashed line that we have here. So they follow each other very well, quite well nicely, but then you also have to remember, which you cannot since I did not tell you, I'm only looking at 2 years. So if you look at a longer time run or model run, then you would have these two curves. So the residual, the thick black line, and the gray dashed line, they would follow each other a bit closer than they do here. Okay, but just for the second line here to kind of try to show you what this actually means in a more visualized way, I will try to make a short sketch. Okay, so everyone in the room and online should be able to see this. I will try to sketch it very big. Okay, so we have this same sketch again in XZ direction. Let's just do something like this. And this is the bottom topography. And we have all the isohalines shaped like this. And then we have the freshwater.
A pen in a different color.
Yeah, I know I only have the gray one.
Oh, okay.
Sorry, the green one. I didn't find there are only 2 colors.
Try to make lines.
Yes.
That's why the chalkboard is the best.
Yeah.
Can someone online tell me if you see something or not at all?
Yeah, now after the lights, I can see better.
Okay. Well, let's try to do it this way. So we have the incoming fresh water from the right. We can also have the net, well, the precipitation coming in here from the atmosphere. So here in this first soil class, we have fresh water coming in, and these isohalines, they actually, well, they do move a bit with the flow, but if we take a long enough average, they do not move anymore. Then they are fixed in space or stationary. So what really has to happen is that the inflow has to go out through the isohalines, and it can only do so by going across the isohaline. I think I mixed up some words there, but so we have the inflow, but it has to go through the isohaline. So that is just the outflow, the net outflow, and that's exactly what we saw in this figure here. So just that, basically just that the outgoing here is bigger than the ingoing or incoming. Okay, so let's continue with the integrated mixing, and I will see if I can do this. This is der oberste.
Der oberste, ja.
Okay. So now we're looking at the integrated mixing for salinity class. So this, let's say the weird M here. So we have it here, the value along the salinity axis. And we have a lot of things in the same figure, but let's just focus on the thick black line. And that is the mixing that we actually calculate in our model. And it follows the so-called universal law of estuarine mixing, which you can see down here, this formula, quite well. So this is the gray line that we see here. Yes?
It's the point from before, right? It's not universal. If you have only salinity with the special units, it's not so universal.
Yeah, that's something we can discuss. So if we compare the two lines, the thick black line and the gray dashed one, then we see that especially for the lower salinities, they follow each other well, and then we have deviations going towards higher salinities. Yes?
So for each point in the x-axis, it's an integration of that isohaline for that salinity, is it?
Yes, but it's in the x and y direction. So over the whole Baltic Sea.
Yeah, sure, yeah, okay.
Yeah, exactly. So that's why, yeah, the XY direction disappears then. That's why it's an integrated mixing. Okay, so reasons for the deviations that we see between the two lines. Let's just observe that there are other lines, but focus on those two, and we can take questions about the other ones later. But deviation that we have is also because we have this intermediate case where the isohalines start extending outside our model domain. And then we also have the fact that we're only looking at the 2 years, the 2-year model run. And that's why the storage terms, they do not vanish, they do not become zero. So if we take a look at a longer model run, then the two curves should follow each other should follow each other very well, since that's also what is in the theory for the derivation of this formula, that you have to look at a longer time scale.
Argument out there. Larger.
The first part?
Partially outside modeling phase.
Yes, so this is just sketched here, kind of blended out, since then the universal law, so you can't really compare the universal law and the calculated integrated mixing from our model run really anymore, since they do not describe exactly the same thing anymore. That's why it's blended out. Yes, I'm sorry. Yes, it's the first part here. The isohalines being partially outside.
Salinities that doesn't hold that argument does not hold for salinity smaller than that.
Okay, there are also other reasons, additional reasons.
It's maybe also interpolation error.
Yes. We're taking notes. Okay, but you probably noticed that we have the physical extent here, or the physical contribution and the numerical contribution. I won't go into detail here for this plot, but we will show this, or I will show this for our maps. So what we can do in our model at IW, in the Gettin model, is to exactly make these diagnostics, or we can exactly look at the contribution of the physical and the numerical addition to mixing. So the physical, what we call the physical mixing, is due to the diffusion taking place, and the numerical mixing is because of the advection scheme in the numerical model. So we can separate this, and then with this third relation that I showed you before, we can do this then for the mixing on the right-hand side. But then we can also, from the right-hand side, find out about the approximate diahaline velocity, or the physical contribution to the diahaline velocity, or just a general circulation then, and the numerical contribution. So first, before we look at what we call the physical diahaline velocity and numerical diahaline velocity, look at the maps again, but for the physical and numerical mixing per salinity class. So you have the same structure again here, the upper panel being then in this case, the physical mixing per salinity class, and the lower panels, the numerical mixing per sol class. And we have the same 3 isohalines. So these are isohaline surfaces for 5, 7, and 11 grams per kilogram. And the main message that I want to show you here is just that ideally, the lower panel should just be white everywhere, but it is not white. And we can actually see that also here, the numerical mixing is quite strong in the Baltic Sea, for instance. So it's not negligible. That's already something we can see here. And when we take a look then at the physical numerical diahaline velocity, we see the same picture here, that we can for sure not just ignore the numerical contribution to, in this case, the diahaline velocity. So that means just the general diahaline circulation that we have in the Baltic Sea. And yeah, if we integrate this then across the entire Baltic Sea again, we gain this different picture, different in the sense that it's not a map anymore, but actually the same picture. So that again, the numerical contribution is not negligible. So to put this in more relative terms, we have calculate the relative numerical contribution, and you can see that for most sol classes, so here that's the outgoing and incoming numerical contribution. So both are here somewhere around 50% for most of the sol classes. So it's actually really big. Okay, so that's a very important point of the talk, that we definitely cannot ignore this and we should look at it further. And coming to the last part of the results for this talk is the diahaline boundary mixing, which is something I have not mentioned yet, but we will take a look at this now. So here again, we have a zoomed in view of these maps ahead of the entire Baltic Sea in the beginning. So here we have the diahaline velocity, and here I've chosen the 8 grams per kilogram sol class in the left and the 10 grams per kilogram sol class to the right. And we have all these structures. So the picture is very complicated since there's so much going on. But if we zoom in here, for example, then on the Gotland Island, we can see that there's all these enhanced values following the coastline. And we have a specific structure. You can also see it here along the Swedish mainland. So we have the incoming velocity here, which is a lot stronger than in the surrounding areas. And then we have this band of outgoing velocity. And we also have it around Gotland, but it's a bit more difficult to see with this isohaline that I've chosen. But you can see it more easily around the island here to the northeast of Gotland. So we have the same structure again with the red that is in the inner band, and then the blue band that goes around it or is outside of it. So first incoming close to the topography, and then outgoing velocities outside of it. So we can also see this, for instance, here around Bornholm Island, the same feature. And yeah, we can, so what is actually happening is that when the isohalines touch the boundary, the bottom topography, sorry, that's when we would have let's see, then we would have the incoming velocity, so that's red here. So for example here, but then when the isohalines come up to the surface, so as is the case here in the Baltic Sea, then we have all these outgoing velocities. So this is just a different view of seeing where the circulation in terms of an isohaline, and if the isohaline touches the bottom, then we have the intense incoming velocities there. And when the isohaline reaches the surface, then we have the outgoing flow. And yes.
Woodland, that's different, right? That's different. So,
Yes, there's so much occurring that it's difficult to really look at every single space and explain what's happening. But yeah, there is a lot of other things going on. But do you mean the structure that we see here?
just asking if the
Or this?
A lines are autotropic then.
Oof.
Is it also touching the bottom? So
I mean, I would really have to put transects all over the place to really confirm it. So I can't really say for sure. So that's.
looking at the difference.
Yeah. Okay, but I mentioned that this part of the talk would be about boundary mixing, but here this is these enhanced values of the diahaline velocity that we see here along the boundaries. And through my talk, I hope you have gained kind of this understanding that the two are connected, the mixing and the diahaline velocity, so the flow. And just to show you also the mixing then, so these zoomed-in views of the total mixing per salinity class, just to show you that it's also, the mixing is actually enhanced along the boundaries in the same areas as where the diahaline velocity is enhanced. But what I want to show you now is if we take a look at these transects. So in the paper, we look at two different transects, but here we'll just look at this transect number 1, so between Gotland and the Swedish mainland. So we do that in these 3 panels here. So just for the orientation, in the left part of the plots, that's starting here towards the south and then going northwards. So this is towards the north. And in the first panel, we have the diahaline velocity. And then also, this is connected to the salinity gradient then, through of the mixing, through the relation that we saw before, which is also here, if you have already forgotten about the relation. So these we show in the 2 panels here, and you can see again that they are very similar. So again, the diahaline velocity is a bit noisier, but the overall structure we can see here is very similar. And once again, the total mixing, so the mixing is also enhanced in the same regions. And this is all in salinity space. We can also take a look at the same transects, but in physical space. So then it's easier to see now how it relates to the bottom actually. But the structure in itself, as you can see, it's very similar. So we also have this structure with the incoming velocities towards the bottom. So along the topography, and then the outer slice, which is the outgoing velocity. And in an attempt to explain this, we have a sketch here. So we have the incoming velocities here in the bottom boundary layer, and then the outgoing in the layer above. And this is a sketch that is adapted from the big world ocean circulation studies. So one from Ferrari et al. And we see the exact same structure here in the Baltic Sea as well. And through the relation that we have derived, we can see how these two are directly related. So we can see that, so actually here the mixing, the curve here, the local mixing per salinity class, when we go further away from the bottom, the mixing increases, but the salinity is highest at the bottom if it's stably stratified, and then the salinity decreases. So in the end, del M del S would decrease as we go away from the bottom, but then at some point the mixing will start to decrease, and then it will be, well, the sign will be in the other way. So that's why we have this well, that's just the idea of this structure. And this is also goes back to a very old study, or not very old, an older study by Garrett in 1990. So we have this structure that we can see, and this actually shows that the local diahaline mixing per salinity class and the overturning circulation are connected, or that maybe even drives the overturning circulation. Okay, so there has been a lot of information during my talk. So let's see if maybe we can keep these 3 key points after the talk. So on the last slide, we saw this sketch, and that's the local diahaline mixing per salinity class and the overturning circulation are strongly connected, and that the first might even drive the last. And we also saw this plot, and that the spurious numerical contribution to the total diahaline exchange flow can definitely not be neglected, since it's very big, the part it plays. And we also saw that we can visualize these hotspots for the diahaline exchange flow, and that they're located where the isohalines touch the boundaries. So it can be the bottom topography or the surface. And with that, I would just like to say, to finish with my presentation, that we have done this with Baltic Sea and also for the case of diahaline, so the local diahaline description, but it is very important that we should extend this to also the diapycnal, so including the temperature, and for the global circulation. And it is also very important that we find out more about the numerically driven global circulation, so that we can really find out how reliable our climate models is, or this particular part of our climate models. So with this, I would like to finish my presentation. And if you have more questions, then I will take them now and try to answer best I can. And here you have the link to the manuscript that is already online, but not finished. So it's not been published yet. So thank you.